Aloha, Phenomenal Phoenixes. Yesterday, we looked at the ratios. And sometimes those ratios could be like let me get a different color. The original length of something to the image, right? A ratio of the original to the image. It could be like, yesterday we talked about like the distance between the eyes in the original and the distance between the eyes and the new one. Well, listen, that should be the same ratio. That should be the same relationship as the width of the face in the OG and the width of the face in the image, right? And then we also, so that's looking at the relationship from original to image, but we also looked at yesterday the relationship between, well, let me give you a standard thing, okay? Like let's say we have Aloha, Phenomenal Phoenixes. Yesterday we talked about ratios. Ratios have a fraction line like this, and they denote a relationship between measurements. So like, for example, if I have a large original triangle, and then I shrink it into an image triangle, and we say that this is like 12, and this is 6, and this is 16, and this is 8, okay? Then here's what we were talking about yesterday. Yesterday we were saying, hey, from bigger to smaller, from original to image, we have this relationship where that corresponding side, the tall side, the height side, it has a relationship. It's a 12:6 relationship, all right? And what we were, and that relationship is called a ratio. And that you can read it just 12 divided by 6, 12 divided by 6, and that ratio is 2. Now, what we also learned is, whatever that relationship is from original to image should hold up on other parts as well, on all parts actually. So from 16 to 8, it should hold up on all parts if the scaling was done proportionately. And so here we have another ratio, a 16 to 8 ratio, and that is also 2, right? 16 divided by 8 is also 2. That's what we learned yesterday. But today, guys, and then also that was our original to image relationship. But we're also going to talk about, we also talked about length to length, meaning within the same shape, length should hold the same relationship. The height to shadow relationship, we could say, is a 12:16 in the original image. Okay, so within that image itself, the height should keep this proportion of 12:16, this ratio. And then the image, its height, if it was scaled properly, it should have that 6:8 ratio should equal that 12:16 ratio. And sure enough, it does. This is 0.75, and this is 0.75. So you can see the scaling was correct. Now, we are focusing today on the scaling factor, which always denotes multiplication. I know I talked about division, but that was just to get you the idea of it doesn't really matter which direction you go. But we're going to start moving towards realizing that the scaling factor is always multiplication, and it always goes from original to image, which sometimes you decide. Sometimes it's not clear what's the original and the image, and you're just gonna have to decide, right? Like our tree example yesterday. You couldn't say that the tree was the original and the person was the image. We just decided. But it's always multiplication. It's always from original to image. So where do we see the scaling factor here? Here we have the original height going to the image's height. That's a scaling factor. Here we have the same thing. The image's height going to, sorry, the original's length going to the image's length down here at 8. All right. So what we learned today is that those scaling factors, if they differ, it's disproportionate. They need to be the same. That makes sense, guys. If this triangle is shrinking by half, then everything needs to shrink by half. So how do we find this scaling factor? Well, the idea is I need to multiply 12 by something to get 6. I need to multiply 16 by something to get 8. If you don't know that, then the shortcut is just this. Just remember this. Just like use easy numbers, guys. This is so important. If you're not sure how to do this, just say, well, okay, if I knew I had to do like 2 times something to get 10, oh, that'd be 5. So like, how would I find that? What would I put in the calculator? I would do 10 divided by 2. And then that would give me 5, right? So it would take this answer and divide it by this factor. Same thing here, guys. I'm going to take that answer I'm going to take this answer, which is 6, right? Because right now we're saying, right now the real thing we're looking at is 12 times something is going to give me 6, right? All right, so now 6 is the answer, and I'm going to divide it by 12 in the calculator, and that will give me 0.5. And if I do the same thing over here, you'll see it's the same thing. So the scaling factor is times 0.5, times 0.5. To go from original image, we're multiplying by 0.5. We're shrinking this image by half. All right, so let's look at some more examples of this. All right, so we looked at 2 equations of ratios. We looked here where we're looking at the relationships from original lengths, like the original arm length right here, to the image length of the arm, which is 2. So we went from 0.7 to 2. And we got ratios yesterday. I think it was 0.35 was our ratio. But today we're looking at scaling factors, meaning how much is it shrinking? How much is that part shrinking or growing? All right. It's different. A ratio is the relationship between the numbers. Scaling factor is how much it's growing or shrinking. Okay. So we found the ratios yesterday. Today we're looking for scaling factors. So we're multiplying 0.7 times something to get 2. So the reverse of this is to do in our calculator 2 divided by 0.7. And that will give us our answer, which was, give me a second. Okay, yeah, I was right. It is 0.35, 0.35. And so what that means is we are to go from this arm length. Let me double check this. 2 divided by 0.7. That's right. My bad. That's wrong. Okay, it's 2.86. I knew it. And the reason I knew this, guys, by the way, and I'm not going to erase this because I want you to see this. The reason I knew it is multiplying by 0.35, guys, that doesn't make an arm bigger. It's got to be bigger, right? So I got to multiply by 1 to be the same. I got to multiply by more than 1 to be bigger. So I know that can't be right. So sorry, my bad. It's going to be times 2.86. Yeah, it's 2 divided by 0.7. Okay, cool. Now, what about the factor? What do I have to multiply 3 by to get 2? So I'll do the same thing. I say 3 times something is going to give me 2. Well, I'm going to do the opposite. I'm going to say, well, okay, I have 2. I'm going to divide it into 3 groups, right? How much is in the group? And so the answer is 0.66. So you can see here, the scaling factors are not the same. Going from this waist to this waist, we're getting smaller. We're shrinking by 0.66. But to go from this arm to this arm, we are getting bigger, more than double. We're more than doubling, right? Almost tripling our size. Please make sure you're grasping what's going on here and ask me if any part of this is not making sense. Okay, to wrap up this video, let's just look at these other ones. So we have also here, we're looking for a scaling factor, but we got to be careful because when we're looking at this relationship of the length of something and something else within a shape. So the relationship between the arm and the waist in that original guy, that relationship, we have to realize the scaling doesn't go this way. There's no scaling from 0.7 to 3. This is the arm, this is the waist. The scaling goes this way now, right? If we're looking at this kind of relationship, we're saying the 0.7 is growing to the 2. The points of the arm is going to the arm, right? So the relationship we're looking at is the length of the arm relative to the waist. And if this was a proportional image, that relationship would be the same, right? But it's not, it's clearly not. Now, when we're looking at the scaling factor, we got to make sure that we're always going from original to image. The image that's being created by our scaling, all right? And you'll see it's the same because this would be 0.7 times something gives us 2. That's what we figured out over here. So that'd be 2.86. I don't have to recalculate it. And same thing here. It'd be 3 times something to give me 2. And that'd be times 0.66. So you don't have to recalculate. The only thing to just really remember is that scaling is always multiplication, and that scaling always goes from the OG to the image, no matter what. Even if it's like OG over image, the original over the image, that's where your scaling factor goes. Or if image is first and the original's over here, scaling factor still goes this way, and it is still always multiplying by something to get that image. If you're making it big, if you're making it the same size, it's a 1, right? So the same size, you multiply by 1. If you want to make it bigger, you want to make that image bigger, you're going to scale it times more than 1, right? And if you want to make it smaller, you're going to make it like, you know, not 0, a little bit more than 0, but it's going to be less than 1. So somewhere between 0 and 1 if you want to make your image small. We won't talk about what the negatives do. Those are fun debates to have later. Please, guys, if you have any questions, I'm here for you. Let's get this. You got to understand this. Believe it or not, this is going to apply to a whole load of things. Everything from finding the heights of things to finding missing sides. This is what surveyors do. This is what engineers do. Also, later you're going to see this applies to bedding and cells and unit conversion. These ideas, if you really get this, go very, very, very deep. You can solve very complicated problems if you just understand these principles I'm trying to get to. All right, good luck today.